Hi all. So if you're watching this, you probably recognize this as the computer from Ben Eater's very excellent videos about how to build a breadboard computer. And I wanted to talk about this little module that I added down here. And what this does is allows this Arduino Nano to program the RAM in the computer. In Ben's videos, he actually uses this Arduino to program the microcode EPROMs, which you can see right here above it. But I've actually repurposed that, and now I can program the RAM without having to put programs in through the dip switches, which I find a whole lot more convenient. So I'm going to go through and talk about the hardware and software, and then when we're done with that, I'll actually show this working. So first I wanted to talk about the hardware implementation, and then we'll go over the Arduino sketch and see how that works. The idea for this actually mirrors very well a technology called DMA, or direct memory access, and that's something that's been around for decades. And the idea is, suppose you have some slow I/O device like a disk drive, or in olden days even a tape drive, and this thing is going to take a while to get the data, and then it's going to be fairly slow about returning the data back to the CPU. Well, you don't want the CPU to have to sit there and wait for the device and then very, very slowly say, hey, you got a byte yet? Hey, you got a byte yet? And there's a couple of ways to approach this. One thing that helps is interrupts, where the device can turn around and tell the CPU, hey, I'm done, I'm ready to transfer data. But that doesn't really always solve the problem of the device transferring data very, very slowly. So DMA is actually meant to address that second problem. And the idea is the CPU tells the device, hey, go read sector 37 off your media, whether it be disk or tape or whatever, and put it at this memory address, and then interrupt me and tell me when you're done. So the CPU promises it's not going to mess with that memory while the I/O device is off doing its thing. And the I/O device, as it gets its bytes off of whatever media it's reading from, it's just going to shove them directly into memory. And basically what it's doing is it's stealing bus cycles from the computer in order to do that. So it might say, hey, I need RAM in this cycle because I have I/O data, and I'm going to like lose the data if I don't put it onto the bus right now. So it actually locks the CPU out of the bus for a cycle every now and then while it fills the memory with the data that the CPU was requested, and then eventually it tells it it's done. So we're going to kind of use that same idea in that what we want to do here is take and computer here is a little ambiguous because the Arduino is a computer, and then we have the computer we built. So when I say computer here, I'm talking about our computer, not the Arduino. So we basically want to take control of our computer away from the microcode and manipulate the bus and the control signals directly. So we're going to be a DMA device and putting our program directly into RAM and not letting the CPU do anything while we're doing that. And there's a couple of things we have to do there. One is, if you remember, all these transfers happen on the rising edge of the clock. Well, we don't know what the clock's doing. We don't know if the user has put the clock into single step mode or if it's running really, really slow. So for the purposes of uploading code into the RAM, we're just going to say, hey, while we're doing this, the DMA device is going to manage the clock itself. Now, this really isn't the way DMA works in the real world. In the real world, it syncs itself to the actual CPU's clock. But in this case, I think it kind of makes more sense for the Arduino to become the clock, and that way it can get stuff into memory a lot faster. The second thing we were going to have to do is we don't want the microcode ROMs to be outputting stuff on the bus. So we have no idea what signals those things are asserting. They could be already telling some other device to output to the bus, like one of the registers. And if they do that, we're going to have a real mess because we want to put stuff on the bus and have it clocked into RAM. So we're gonna have a way for the Arduino to turn off the microcode ROMs and take over the control signals. And then the other thing we have to do is, obviously, we need a way to drive the bus itself. And we need to do that safely, in that we don't want to be able to put stuff out on the bus while the computer is running, doing its own thing. So we're going to go over the circuitry I put together for all three of those things. This here on the Arduino kind of says where these signals are, but we're going to go through these signals actually here in logic. So up top here, the first thing we have to talk about is you probably recognize this as something that's already in the computer. This is the logic part of the 555 clock on the very first module that's built in the computer kit. And normally what would happen is out of this last AND gate, when halt is not asserted, is that this pin 11 would be connected to the system clock, and then I've called that sys clock here, and the inverter here to sys clock B. B is a standard convention, meaning bar used to be, and you'll still see a bar over top of a signal, meaning that signal's inverted. B is used when typography doesn't allow you to actually put the bar there. So sys clock B is the version of the clock that's used to actually drive the microcode, because remember, we need to set up the microcode on the opposite clock cycle of actually doing it so that the correct control signals are asserted before we actually make our transfers. So instead of allowing that to go right through to sys clock, we're going to add another few gates. And there are actually enough unused gates in the chips that are on the clock circuit that I was able to build all this without adding any new chips. So the pin numbers here, if you built the clock the way it says in the instructions, you should have all of these pin numbers free, and you should be able to just like build this by adding a couple of wires. So the two signals we're adding are ACEN and A clock. So ACEN means I want the Arduino to take over the clock signal. You can see that's inverted, and the inverted version of that is ANDed with the original clock. So if this signal is asserted, then this is going to be 0, pin 9 going into this AND gate, and the original clock is not going to make it past this AND gate. And then we have this OR gate, which combines that clock and A clock, which is the clock coming out of the Arduino. So there's no inverter going through an AND gate here, because we figure the software in the Arduino is smart enough to not go start messing around with A clock unless it's already asserted the enable. And after that, then we put that back to the normal system clock and the normal clock for the microcode. In that case, we're not going to really need this because we're not allowing the microcode to run anyway, but there's no reason to mask it off. It doesn't hurt anything for this clock to still be running. So another thing that you're going to notice is on a bunch of the signals that come out of the Arduino, they have pull up or pull down resistors. You know, so there's two 1K pull down resistors on these lines. And the reason I did that was I wanted the computer to still work even if the Arduino was powered off. If you have the Arduino hooked up, it's generally not considered good practice to have power connected to the Arduino through the power pin and also have power connected to the Arduino through the USB cable. And normally when we're messing with this, we're going to have the USB cable on the Arduino connected to like a computer, because that's how we're going to write code. We're going to write it on a desktop or laptop computer. So I wanted the circuit to work even if the Arduino was turned off. So say even if you yank the USB cable out of the Arduino, then the signals that would be driven by the Arduino should be in a reasonable state and let the computer run. That also means that if we want from the Arduino side to say, hey, I'm done, I don't want to like mess with this anymore, and we'll see this in the code, we can tell the Arduino, hey, all of these pins which we've been using to output and drive the computer's bus, we can say those are all now inputs. And the effect of that is that it will, from the computer's point of view, it will put those pins in the high impedance state. That basically means they're floating. And then the pins are going to do whatever they're going to do as if the Arduino wasn't there anyway. So in this case, the important thing is that we want the enable to be pulled down because we want it to say, hey, the Arduino was not driving the clock. And then we also want the clock line to be pulled down because we don't want spurious floating pulses to be injected into our clock train because that line is floating. So that's pretty much the the design of the things that have been added to the clock. You see, it's pretty simple. It's only like 4 gates. So for the ROM, which we have right here, I don't know why this is scrolling so slowly. I'm sorry. So this is pretty simple as well. So in the original design, we always wanted the ROMs to be. There's no reason not to have the ROMs have their data lines always outputting. As remember, these are the 2 microcode ROMs. So these signals, D0 through D7, these 16 signals between the 2 ROMs, go to the bank of microcode LEDs and also to the control signals for the rest of the computer. So normally you'd never want those to not be telling the computer what to do. But in our case, we do want to take those offline because we're going to drive the microcode signals from the Arduino. And I don't, if you can see here, the only 2 signals we're going to care about, it just went off because the title bar showed up. But the only 2 lines that we're going to care about are MI and RI, which makes sense because MI is load the address register, memory address register, and RI is load into RAM. And everything else we want to be low. And if we take these ROMs offline, then all those LEDs with the resistors on them kind of act as a natural pull down. So you'll see that if you take the ROMs offline, all the control signals go to 0, which is exactly what we want without any additional work. So all we have to do is connect that output enable with a pull down resistor to another pin on the Arduino, and we have a way for the Arduino to take those ROMs offline, but normally they default to their state of being online. And then we have, so if you read the section at the very end of the kit and built the Arduino EEPROM programmer, you'll probably recognize this setup, and it's for the exact same reason. The Arduino that came with the kit, so I actually just reused the Nano that came with the kit because I actually have a USB EEPROM programmer, so I didn't need to use the Arduino one that came with the kit. But the same principle applies here in that there aren't enough lines in the Arduino to drive all of these other things we're talking about, to drive the clock and drive the ROM enables and the control lines, and also have 8 bits left over to drive the bus. So we're going to do the same thing and use this shift register. And in fact, this is the exact same shift register chip. In fact, it's repurposed because it was provided in the kit for the EEPROM programmer. And here, the only difference is instead of this thing going to an EEPROM to be written, these lines, we're going to take the output of the shift register, the parallel outputs, and just connect them to the bus. And that's okay because there's this gate input to the shift register that says whether or not the output is tri-state or whether it's actually driving the bus. And this is an active low input, so here we have a pull up resistor to say that when the Arduino is not there, then we don't want to be asserting these signals on the bus. And then we have this BOE, bus output enable, that will allow the Arduino to take over the bus after it has safely disconnected the EEPROMs from the bus. And finally, by the way, I didn't show a schematic for the MI and RI lines, but you saw where they were at the top of this. And if you don't worry, if you didn't get from watching the video what pins all of these lines were on, I'm going to put a link to my GitHub on this, and GitHub has the Arduino sketch, and it also has this PDF, so you can see where I put everything. So the last thing we kind of want to do is, it would be nice once we load the program into RAM if it just started running. So basically we want the Arduino to be able to press the reset button on its own. And here I actually did add another OR gate. So I just added this OR gate, and on one side it's got a pulled down reset line that goes to the Arduino, and on the other side this is the exact same switch setup that was already in the computer, with the only difference being that instead of going into this NAND gate, or AND gate, that it's going to go through this OR gate first. So either pressing the button or the Arduino going and resetting will cause the computer to reset. Okay, so that's the hardware. It's pretty simple. All of this fits on one breadboard, and I'll actually show a video of it working after we go over the code. But yeah, let's now go and take a look at the code. Okay, now that we've looked at the hardware, let's go through and take a look at the sketch to drive it. And similar to the way that the EEPROM programmer in Ben Eater's project just included the generation of the microcode in the sketch, we're also going to include the source code that we're using to program, the assembly code, sorry, to program the computer directly in the sketch. So up top here you can see, as in most Arduino projects, these are all the signals that we've defined in the hardware and what pin they map to. So I'm actually going to jump to the end for a second here and look at the setup. This is our main routine, and if you notice, our loop routine here does nothing. So when we reset the Arduino, it's just going to program the computer and then stop. We don't want it to do anything ongoing. So the setup routine it says what we're going to do. We're gonna take over the bus from the computer, from the microcode. We're going to, so the 16 here, I probably should use a constant there for readability. The 16 is the number of instructions we're going to program. So for each instruction, we're going to put I on the bus. So here I is the address of the instruction that we're going to write, and we have 16 instructions, and the addresses of those instructions are 0 through 15. And then we're going to clock the MI line. Now remember, the MI line is the memory address register. So that instruction is going to put I out as the address that we're going to write to RAM. And the next thing we're going to do is we're going to put an instruction. This array program, which we'll get to in a little bit, contains the actual assembly code, or at this point machine code, that we want to put on the computer. And we're going to put the byte at address I onto the bus. And then we're going to clock the RAM input line, which will write that byte into the address that we previously just clocked into MI, or into the memory address register. And once we do this 16 times, then we have completely filled the computer's RAM with our program. And we're going to reset. So what reset does is it's going to trigger that reset circuitry that we built that will reset the whole computer and start it off at instruction 0. And then we're going to release the bus. So once we release the bus, what happens is dependent on what the user is set up the clock to look like. If the clock is turned on, then the program is just going to run. If the clock is set to single step, then you're all set up and you can start pressing the single step button on the clock and step through whatever program that you've used this to put out on the computer. So let's go back up to the top and look a little bit about how we do these things. So first we have takeover bus. And this is setting the initial states of what all the pins are, and then we're going to set all the pins to output. So this is kind of, I think, good practice in general when you're writing Arduino code. So we don't know what state that these pins are in when we start, but if they're in the input state, and then we set them to the output state, well, that pin is going to be in some state. And if we do the pin mode first, then we're going to get whatever happens to be there out on the pin, and that might not be a good thing. So if you do the digital write first, so that will internally in the Arduino set the flip-flops that are attached to all of those pins to the high or low state that we want. And then when we turn them to output, we know that the line will immediately go to that state without glitching out and going to something that might have been in that flip-flop that we don't know about. Again, this probably isn't going to cause problems, but it could. Release bus, that's just the opposite of takeover bus. Basically, we're just going to set everything back to input, And that's going to cause those pins to go in the high Z state where they're not driving these lines at all. So at that point, these lines are going to go back to whatever the appropriate pull-up or pull-down resistor that we put on them is, or if there's, since we're turning the EEPROM back on by releasing the line. So the this ROM enable line is no longer asserted by the Arduino, the microcode ROMs are going to start driving MI and RI again. So after this, everything will be back where the components of the computer itself are going to be driving all of these signals that are important. Put data on bus. So remember, this takes this data, and really we only care about the low 8 bits of this because the bus is only a byte wide, and this is going to put this on the computer's bus. And if you remember, we had that 74595 shift register because we didn't have enough pins on the Arduino to just connect the bus directly to the Arduino. So here, what we have to do is we have to shift the data out, and we have to remember to do this in the right direction. And the first thing that we shift in is going to end up in the high bit register on the shift register. So we want to actually shift this data byte out high bit first. So you can see here, we're actually in the beginning of this loop is going to loop over all the bits in the data that we want to send. So the first thing we're going to do is actually write the high bit of whatever is in that variable out to the serial data line. And then we're going to shift it left by 1. That's going to take the next highest bit and put it in the high bit. And by the time we're done, the low bit of data is going to be the last thing that ends up in the high bit and to be sent. And then here, all we're doing, so remember, SR clock is the signal that tells the shift register to take something from the serial data line, move all of the bits it's already got over by 1 to make room for whatever's on the serial line right now. So by the time we're finished with this loop, the byte in data is going to be in the byte register inside of the shift register and is going to be ready to be sent out on the bus. So the shift register actually has 2 clocks. SR clock is the one that tells it to take in serial data, and R clock, which we're toggling here once we're done with all the shifting. R clock says, hey, take what's in the shift register and move it to the output register so it'll drive the actual output pins on the chip. So at this point, and the reason for that is, again, this boils down to the same thing we talked about with takeover bus. You don't necessarily want all of those bits going out, like each time you shift to have all of those lines change. You want to have control and change them all at once. And that's what this is doing. So when we assert and take back down our clock, we pulse that clock. What we're doing is all at once putting the data we shifted out on the computer's bus. And after we run this, so now we have either the address for the MAR or the data is on the bus. So now we have clock. We can explain what clock control line does. So remember, what comes in here is either MI or RI. These are the pins that are actually connected to the control lines that normally the microcode ROMs drive. But instead, we want to drive them here. And we know, because we designed and built the computer, that those control lines are acted upon by all of the modules in the computer on the rising edge of the computer's clock. Well, we now are the computer's clock in this code. So what we want to do is we want to set that pin for whichever module we're talking to, the MAR or the RAM itself. We want to set that to high, and then we're going to simulate a clock pulse. We're not simulating, we're actually going to make a clock pulse. So we're going to set the A clock line high, which, remember, now that we've enabled that, is actually connected to everything on the computer's clock bus. So we're going to put that high. I just put this delay in here because the clock normally runs a lot slower than the Arduino's clock. The computer's clock runs a lot slower than the Arduino's clock, so it just seems safer to wait a little bit to make sure. I didn't try it without the delay, but with the delay it works, and the delay is only 10 milliseconds. So it's not really enough time to even notice when you're loading the program out there. So this rising edge, the MAR or the RAM is going to take action on whatever's on the bus, and then we're going to put the clock low again, so the next time around we can set it up again, and then we take the pin down, so next time it's not accidentally still asserted. So the only thing we have left in the programming now is this reset, and again, the reset line is not actually a clocked line. The reset is asynchronous to everything else. So we're going to do the exact same thing. We're just going to pulse the reset with a 10 millisecond pulse, which is equivalent to somebody very, very quickly pressing and releasing the reset button on the computer itself. And that's going to reset everything to 0, and then we're ready to roll with the program. So the only thing we haven't talked about here now is the program itself. And I mean, we could write an assembler for this assembly language, but it's so simple that it doesn't seem worth it, at least not yet. So I just wrote some old school C macros for all of the instructions. And if you haven't changed the microcode of your computer from Ben Eater's videos, then this is the exact same encoding that he put all the microcode instructions. Obviously, if you've changed or add more instructions, you can just either add more defines, or, I mean, this binary here, all these binary constants should look very familiar. Like, you can just change these to whatever you actually called your instructions. And then the program array is then just every entry in this is just calling one of these macros, and if the program takes an address or a constant, then the macro takes an argument that takes that, for instance, like LDI here. LDI is load immediate, so load immediate 1 is going to put 1 in the A register, then we're going to store that in memory address 15, we're going to output it, and obviously add 15 is going to add 1 to A, and then, yeah, I mean, this should all look very familiar. So this, by the way, if you look at this, we're jumping back here to 2. This is actually going to put powers of 2 out on the display. Because here we're going to output 1, and then we're going to add, and we put 1 and 15. We're going to add 15 to itself, and that's going to get 2. If it overflows, we're going to start over. If not, we're going to put that 2 back in 15 and jump and output the 2. And then we're going to add 15, which is now 2 to 2, and get 4, and so forth. This is basically a different program, so we can demonstrate that we can actually upload a program we haven't seen before using this code. And then we're back to setup, which we talked about before. So now let's go and see what this looks like when we actually run it on the computer. Okay, so now let's see this in action. So I am going to plug in the computer here. Sorry, it's hard to do this while the camera is running. And I have the clock turned off right now, and we are going to on here. So I already have this programmed with the program that I showed in the Arduino sketch. So I'm just going to hit reset here on the Arduino. And you can see that little bit of flicker. That was the Arduino driving all the control lines and putting the program out there. And now I'm going to turn the clock on. And you can see it start to run. And here we go. Here are our powers of 2 as promised, over and over again, so it works. So I hope you enjoyed this. I'm planning on doing more of these videos because I really enjoy adding new features to this thing. So please like and subscribe if you want.